I do think we're sort of live. So, hi everyone. Hey, welcome to my stream. My name is Zach, and I should probably announce on the group that this is live. This is live now. Yeah. It's live now. Yeah, so basically announce it, it's live. So let's see. I think so. What I sort of want to do today is for my own benefit and for the benefit of everyone in my group. I would like to go through some camera sensor basics within the last few in the last few months or in the last month or so weeks. We've been working a lot on image sensors. And I'm getting to a place where I'm doing quite a bit of complicated work with image sensors right now. And for my own benefit, I want to go through this document, and I thought, what better to do it? And I think it makes sense to go through it with everyone involved in my group, and you guys and people who watch this, and maybe we can explain some stuff, maybe we can learn some stuff together, and see where that goes. So I think I'm going to do something sort of, I'll get some water first. I think I'm going to do some sort of maybe an hour and a half of a stream where I go through this document, and I might have to run through some examples here and there, but the main objective of now is to sort of understand how camera sensors or image sensors work at a very low level, and basically make it possible to start, to join up and start using them. I didn't know that was that little one. So, I'm just gonna go on an overview, gonna understand some terms, and sometimes it's just that we need to understand terms before we can actually do. Understanding the terms can at times be more difficult than the actual work that it is, And once you understand the terms and where to plug them in and where they go, it's the same as mathematical equations. Once you understand which terms, what symbol means what, and where it goes in the big picture, then it becomes really, I say it becomes rather easy to compute whatever you want to compute. So we might not even get a chance of jumping into code or doing something of the sort. We might just go through this document and have a discussion about it, and I invite questions from you and from everyone who's watching. And if you have any more questions, you can look in the description. We should have a link to a Discord channel, and you can join us and ask as many questions as you want and basically explore with us and see what happens. So let's actually go through this and see what we can surmise. So I'm going to do a little bit of a zoom. Not Black Friday yet, it's probably soon though. A little bit of a zoom here so that we can actually see maybe a little less, so everything is in the screen. Cool. So just going to read through this. I'll be stopping and explaining, and if anyone has any questions, we can kind of sort of ask them. So this wiki describes the relevant concepts dealing with camera sensors. It represents a useful handbook, especially when it becomes to developing drivers for camera sensors, and the concepts explained here are not attached to any specific sensor or any custom hardware board setup, so you could extrapolate this information to whatever you're working on. And that's actually what made me want to do a stream of my study on this, because this is not tied to any camera, this is not tied to any operating system, this is not tied to any coding language or any FPGA stuff. It's just, how does this thing actually work in such a way that if you understand how it works here, you can go out and start doing your own things on your own image sensors, on your own boards, on your own image sensors, boards, and whatever. So let's look at it. The first place this document seems to start with is MIPI. And MIPI is a mobile industry processor interface. And it's sort of a conglomeration. If you know what Android is, like Android open source project is, it's an agreement by a lot of people to make hardware and software in a certain way so that things can plug in into each other very easily. So basically, camera people and mobile people and handheld computer people sort of agree, let's make image sensors work this way, and let's make computing systems that want to interact with image sensors work this way, and that way that you have microcontrollers or boards that come with image connectors and such. And I even have another one on my desk here. I think I'll disconnect the display so that we can actually just lift this thing and it's much easier. I even have another one here. This is an FRDM MCN X236, and it has an SDMA connector for the camera, and it's just a connector for the camera. This is a, what's this thing called? This is a STM32N6, which also has a CSI2 port for the camera, and I have an FPGA here, which is a Tiny Clue NX33, and it has MIPI ports over here for cameras. So basically, there's many ways of connecting your camera to a device, and because of those many ways, all of these people agree on how to make those connections and agree on how the software should work. So that way we can sort of have many cameras interconnecting. And the standard that governs all of this, is called MIPI, which is the Mobile Industry Processor Interface. And it was founded in 2003, and to date it has something like over 300 members. And the focus of the organization is to design and promote hardware and software interfaces that simplify the integration of components built into a device. So your mobile phone, even with the cameras at the back and the screen at the front, will also be using some sort of MIPI standard and such. And so maybe even your laptop will be doing this. Between the webcam and the screen and streaming and all of these things. So it's quite a wide array of things that are involved in it. So it's not just the connector, it's not just the cameras, it's also the gluing code and the gluing hardware that is involved in this. If anyone has any questions, please feel free to kind of chime them in. Okay, so what does the MIPI standard involve? It at the very basic level, it involves connections. So the physical connections between the camera or the image sensor and the processor, which is called the PHY. Or in this respect, we're going to refer to it as a D-PHY, but also there's C-PHYs and such. It depends, okay? But there's a PHY, which is the physical connection. So this is the wires or the links or the traces on a board. This is the connection between the image sensor and or the display sensor and the actual controlling computer. And then there's a display serial interface, and this display serial interface involves itself with displays, as is in the name. It dictates how you will communicate with something that is displaying some data, or some image, or some screen, some interface or so. So the display serial interface defines the data transfer protocol and the interface between a host processor and a peripheral device, in this case a display. And then there's a camera serial interface, which is a CSI interface, and this also defines the control interface, and it defines how. So there's two sorts of interfaces. There's a control interface, and then there's and I need a camera. It would be nice to have a camera to show you this. I wish I could actually it might be. Oh yeah, there's also this. This is an OpenMV NXP MIM RT1060, and it's made by OpenMV Systems and such. So let me find something. Perhaps I can take this apart. Do I have a screwdriver? I usually have a red one on my desk somewhere. Perhaps I can take this. But basically, what I'm trying to show is that a camera has a few. Where's my OV5640? Where's my OV5640? Yeah, here. Sorry. Might be even easier if we just looked at it on the Adafruit. Yeah, this one. Might be easier if we looked at it online, so that way you can see better. You can just see rather than me just trying to show you actual images. Yeah. So let's look at this image. I expect this one's a good image. Yeah. So let's look at this image. So if you can see this image, there's going to be a few. There's a few pins on this camera. I hope you can see. And on this camera, we have a ground and a 3-volt pin, and that is okay. That's just for powering up the device. And then next to it, we have a SDA line and an SCL line, which is for either SCCB or for I2C. Depends on how you want to call it. But it's a camera specific interface that is involved with sending control signals. So telling the camera, start taking frames, set the exposure to this, set the gain to this, set it black and white, set it infrared, whichever one you want, and such. And then there's a H sync and a V sync, which is a signal that displays you've either sampled a whole line or you've sampled a frame. We'll get to this later. And then there's a master clock, which is the X clock, and there's a P clock, which is the peripheral clock. It is for synchronization between the camera and the camera and the host processor. And then next to them, we see there's a power down and a reset buttons, but those are just sensor specific. They're not really control signals. They're just like for this sensor. But what I want you to notice here is that there's a D2 all the way to D9, which is, I think, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, which is 8 signals. So there's there's 8 lines of data going through. And this is going to be what we refer to as the data interface. And then the SPA and the SCL are going to be the control interface. So some of them send instructions to the image sensor, and then some of the other signals are used to send back data from the sensor, not just instructions and such. And that's the difference between the data transmission interface and the control transmission interface. Okay, cool. So that's sort of a thing about MIPI. And then we're going to look at the DeFi. Does anyone have any questions currently before I go on? So I take a sip of water. Does anyone have any questions? You can put up questions in the comments. You can put up questions on the Discord and such. No questions so far. You can say hi as well if you want. Okay, cool. So no questions so far. So let's look at the DeFi. It's called the DeFi because it signifies the Roman numeral 5. D is the Roman numeral 5. And when this thing was designed in the 2000s, in the early 2000s, it was assumed it would carry around 500 bits per second. But however, the standard has evolved, and we are maybe 20 years later after this standard was invented, and actually the maximum rate this thing can do is 9 gigabits per second, which is quite high. But usually, the more interesting part about the DeFi is that whenever you start talking to people who do a lot of camera or image sensor development, they talk in terms. They say these terms that can be very confusing, but they really don't mean that. They're not very complex. They're just very, once you understand what the term means, it becomes very clear what they do. They'll say things like lanes, and then they'll say things like control interface, and they will say things like control path, data path, and things like that. And I'll take you, interestingly, I can take you to the Tiny Clue NX. This is one of devices that I've just shown you, but we're not looking at it. But what I want to tell you is, in the beginning of the description of this device, it says the TinyClue NX is a module built around the lattice crosslink U NX33 FPGA with up to 14 MIPI lanes. You see? So whenever you start getting into like camera interfaces, you start getting these terms and you don't know what the terms mean. And that is what we're going to do today. We're going to sort of break down all these terms so that we understand what they are and we're able to like land into relevant conversations and understand what people are talking about very clearly and be able to catch up and stay on with them. So this is what let's break this down and sort of try and understand what these basics are. So number one, there's something called a line, and the line is an interconnect between the processor and a peripheral device. So this is basically a wire. A line refers to the wire, okay? And then this is going to be between, in this respect, because we're talking about camera basics, we're going to speak about the camera, the peripheral as a camera. And the processor is going to be some sort of MCU or FPGA or whatever you have on the other side that is consuming the data. So a line is going to be a wire that is connecting both of this. And then a lane is going to be a pair of wires. And a lane becomes a lane because a lane can actually support the differential signaling. And differential signaling is basically, I think it's lower, but differential signaling is a noise resistant way of sending data in which you use I forget the term, but the two signals will never be either both high or both low. There will be one will be high and one will be low, and then you use the difference between them to get the bit that you're being sent, rather than the way we are used for single-ended signaling, which is you either get a 1 or a 0, a high or a low. And the thing that makes this differential signaling very good is that it is very noise resistant. It's very hardy, and because if there's some noise on the line, both signals will be affected in the same way, so that the gap between both signals remains the same, and basically you preserve the data you have. And whenever you're talking about sending data over very long distances, 10 meters and higher, things like what CAN bus does, which is you have 100-meter networks in cars, you end up having to use differential signaling, because differential signaling is very robust. Yes, robust is the word. Okay, so a lane is a pair of wires that is used to transfer data or control signals that is capable of differential signaling. We'll see what differential signaling is just shortly now. And a link between two devices is a connection that contains one clock lane and at least one data lane. And I think, let's see. One clock lane and at least one data lane. Let's see. Does this talk about links? No. But you might encounter this term basically. But in order for you to make a link, you need a clock lane and at least one data lane, and then you can connect them up together and such. Any questions so far? Let me answer some messages here. Any questions so far, please? Yeah. If anyone has any questions before I go on, that would be awesome. I'm just taking a picture here, and then we'll go on. Okay. So, no questions so far about a link or a lane. So, the thing that makes MIPI very special, and the thing that makes MIPI capable of this super high rates of data transfer, is that you can do quite a lot of signal multiplexing. So number one, you can send data from more than one peripheral to more than one to the controller. I'll keep it at that. And then you can also send control signals, clock signals, and data signals sometimes on the same line. But it's, in a sense, itself is it's a very simple way of doing things. So it's not so difficult. It's just that the way it works enables it to be able to multiplex. And formally, before going through this document, I knew it could multiplex, but I didn't know how it could. It turns out the way it multiplexes is very simple. It has a few modes, and it can change between modes, and each mode has like different slew rates, and some modes are exclusive of other modes, and some modes are inclusive of other modes, and that's how it ends up becoming very capable of, very capable of doing this sort of very magical data rates, such as, things like this GBPS that you can see. So let's look at it. So there are 4 modes of operation for a lane. And there's a control mode, there's a high-speed mode, there's an escape mode, and there's an ultra-low power state. Data lanes support all 4 modes, but clock lanes basically don't support the escape mode, basically. And during normal operation, a data lane is in control or is in high-speed mode, and high-speed data transmission happens in bursts and starts and ends from a stop state. So, which is referred to as LP11, which is in control mode. So let's look at all of these modes. This image, I'll put it on the screen for a while. But if you look at this image and you keep looking at them, you will realize that this image actually defines the multiplexing. Number one, so multiplexing in ways that you can send a control signal, or rather a data signal and a clock signal on the same line. You see, on the same line, and then you can sort of like figure it out. Okay, so in the DeFi IO pins have 2 different electrical modes of operation. Okay, they can either be single-ended or differential. Whenever they're in single-ended mode, this is referred to as low power mode, and it is using during escape and control modes. So you can set the pin as an input or an output only, and then in this time it can be when it is in this low power mode, LP mode, it is either used for escape or control mode. And control modes is when you're sending some control data. It's like, okay, set the exposure to this, set the gain to this, set the frame rate to this, all of those things. And during this time, it's not in a differential mode. It's basically in a single-ended mode, and because it's in a single-ended mode, it will send data between ground and VDD/IO, and the slew rate. So, do I have? I'll just go here. Slew rate. Slew rate is the speed at which a pin can change modes. In electronics and electromagnetics, slew rate is defined as the change of voltage or current or any electrical magnetic quantity per unit of time. So, how fast it can change this? How fast it can change this mode? So, it changes. It changes the slew rate, which is basically the bit rate, which is basically how fast it can go up or down. And it probably uses a slower slew rate when it's in low power mode, so that it's changing from high to low at a much slower rate. And in this rate, it is sending control mode. So you're setting up the camera. You're saying, this is what I want the black level to be. This is what I want the white balance to be. This is what I want the gamma corrections to be. This is what I want the color correction rate levels to be. But these are all they start becoming ISP, image signal processing things, but they're not necessarily covered in MIPI. But what we do know is they're called control signals. They're control path. You're not this is not where you get the image from. This is where you get to tell the camera how you want it to make an image for you from. Okay, so it's not they're not the image one. When you want to do this kind of work, you will use the low power modes, and you will probably use either 00, 01, 10, or 11, and they're all sort of okay. So 00 LP low, and DP line and DN line LP low. Okay, and then high speed it's not you can't do high speed stuff in low power mode. And then in LP01, DP line is low and the N line is high, and you can use this as a high speed request. And then you can use LP high and LP low. In DP line can be high and DN line can be low, and you can use this as a low power mode request. And then if DP line is low and the N line is high, then you are in stop mode. Basically, you're not doing anything. And also, if you are in some of them can also dictate that you're in escape mode, which we'll cover on later. And then, as you can see, there's HS0 and HS1, and the differential mode is referred to the high speed mode, and it is used for data transfer. And in differential mode, it only has two states, HS0 and HS1. And during HS mode, the two I/O circuits which comprise a lane are always in opposite output polarity, and they can never be in logic high or logic low at the same time. So in HS low, DP line is low and the N line is high, and it is differential 0. And then in HS1, DP line is high and the N line is low, and this is differential 1. And you cannot use control data during these times, basically, is what I'm saying, or is what this document is saying. Okay, and then now we're going to look at the clocking of these signals. Does anyone have any questions so far while I take a sip of water and then we go? Any questions so far? No questions. No questions so far. Let me check the Discord. No questions so far. Okay, cool. So now let's come on to one of the things that makes this thing really fast. Okay, one of the things that really enable MIPI to be as fast as it should be, and also this is the things that kind of, once you start understanding that hardware can do this, it becomes quite obvious how data can be moved really quickly. So there's something called DDR clocking. So data rate clocking. And what this means is, when do you sample the data? And normally we would sample the data either at the leading edge or at the trailing edge of the clock. So is it rising or is it falling? And we would sample the data then. So you're basically saying, if you have some sort of, what did Nathan teach me? Excalibur. If you have some sort of signal, and if you have some sort of, like, let's call it a signal. Let's take a pencil and let's make a signal. Yeah, and then we have some sort of clock down here. Just assume all those gaps are. Assume all those gaps are actual, they're actually the same size, and assume this wasn't drawn by hand by me and stuff. So here's the thing: in SDR or in single data rate, in SDR, you would only sample the data at this point. Okay, so let's pick the leading edge. You see, you'd only sample the data at this point. So what data would you get? There will be no data here. This would be the data. And then what would you get here? You would get this. And then what you get here? You would get this. This is a sample. This is the sample. And this is the sample. and I think this is a sample, and this is a sample. So this is your real world signal. And then let's look at DDR. So in DDR, what happens is you're sampling the data at both the leading edge and the trailing edge of the clock. So you would sample here, 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 and 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 you would sample here. Cool. And what will be the data points be? This one will obviously not be there, and then there will be a half one here, and then there will be one next to this one just there, and then there will be another one halfway to there, and then there will be another one halfway here, and so on and so forth. You see? So there's this. So what we're doing is always in the middle of the signal, there's always another signal. And you see? And then in the middle of the signal, there's another one here between these two, and then this one, there's this one here, and then this one, there's this one here. And what is this showing us? Is that if you have a sensor that can really obtain the real world data really, really quickly, and you can sample it faster, you can sample it at both edges of the clock. And sampling at both edges of the clock is an acronym most computer people will be used to. It's called DDR. You've heard of something called DDR RAM, double data rate clocking. Okay, and a double data rate means you're clocking at both ends of the signal. And here you go. So you see, so in single data rate, this is the clock. You sample here, 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 and sample here, you sample here. And these are, you'll get 1, 2, 3, 4, 5, 6, 7, 8 bits. Okay. And on double data rate, since you're sampling at both sides of the clock, you'll sample here, you sample here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bits. So you get double the data, double the amount of data for the same time, for the same amount of time. And if you have a really good analog sensor, such as depending on the ADC of your camera or of your whatever sensor you're using, if you have a really good analog sensor, what you realize happens is that you can consume data from it very quickly as it gets it. And then depending on how quickly your clock goes, you can keep consuming at it. And remember, like, analog data can be very fast because analog data is sort of like electricity. You don't really have to wait a little bit until the light is on. When you switch on the light, it just goes on. So if you can sample that fast, if you can sample at the speed of electricity, then you're good. And especially when we're talking about optical sensors, So these are things that are sampling at near or like the samples they're receiving are hitting them at the speed of light. So they're getting really a lot of samples, and really the speed depends on how fast you can consume them, not how fast they can get signals from outside. So what am I saying? With DDR, you get double the speed compared to SDR, and this is one of the things that makes MIPI fast. So because MIPI is capable of doing DDR, or rather in high-speed mode, MIPI does do DDR, and because of that, it can transfer images much, much quicker than, say, single data rates. Both CSI2 and DSI specifications support continuous clock mode, and for continuous clock mode, the clock lane remains in high-speed mode, generating active clock signals between high-speed data packet transmissions, and for non-continuous clock behavior, the clock lane enters LP11 state between high-speed packets, and this means that in continuous clock mode, you have higher data rates. So basically, because you're not using time switching clock modes, the clock is always there. So whenever you're transferring data, but whenever you're not transferring data, the clock is still going at the high speed mode, and it just, you don't have to wait for this rise time and fall time for you to be able to do this stuff. And so at the expense of power, at the expense of consumption and budget, continuous clock mode actually does perform way better in sampling stuff. Another water break. Does anyone have any questions so far? So far. Does anyone have any questions? Cool. Okay, so now let's look at CSI2. And CSI2 is basically this little connector and that FPC cable. I'll show you. So this is a CSI2 connector here, and this is an FPC cable that connects to a camera, an IMX2 line. Okay. So CSI, that's basically what is used there. But what is explained there is just it's a camera serial interface. The CSI2 specification follows the same general architecture as the DSI specification. It takes parallel image data bus and serializes it into bite-sized block data blocks for high-speed transmission over on a file, on a physical link. Okay. The biggest difference is the addition of a separate control interface and the support for embedded data in the image frame. So basically, what it's saying is the CSI image allows us. The CSI interface allows us to have a control interface in the CSI interface. Like, it's not just the data, just the parallel lines. It also allows you to have a control interface, and usually this is via I2C or SPI. And then it also supports you as embedding some sort of data inside the data in the image frame. So we can embed the type of image, the pixel type, the pixel counts, the binning mode. It depends. And if you work at a low enough layer, you can basically choose what data you want to embed into this device. And then there's something called the camera control interface. And this is a subset of the I2C protocol. You can find this in Zephyr Video Common. I'll show you. The one easy place to find it is GitHub Zephyr. Yeah, and then I think Zephyr, and then no, not that one. That one's already merged. Sorry. So in drivers, if we go to drivers and we go to video. We go to drivers and we go to video. And we go to common, video common. You would find something called the CCS. There's a CCI library here. So there's going to be this CCI functions. But maybe it's in H or something. Maybe they're not defined here. Yeah, so you see here. So there's video write CCI register and video reg retry, and I think there's video modify CCI register, video write CCI multiregs, video write CCI multiregs 8, multiregs 16, and CSI link and all of those. What am I trying to show here? It's that this is an example of the camera control interface, and it has a standard. There's a way of doing things in it, and because there's a way of doing things in it, you can almost use it as a layer on top of things. You see, you can use it as a layer on top of things, and it can almost in a way become an abstraction between the processor and the image sensor or image sensor that you're wanting to use. And it's basically a subset of the I2C protocol, but it's a subset of the I2C protocol, which also depends on another subset of the I2C protocol called the SCB interface. So there's the SCCB, serial camera control bus. So this is just a way to talk to the camera of I2C that was defined by OmniVision, and a lot of people use it these days. It is, I think it is number one, it is pin for pin and message for message compatible with I2C. And anyways, the way, if you look at the timing diagrams, this is just I2C. It works almost the same. It just has some caveats. That's it. Can we zoom in? Yeah. So there's the clock lane, and then you have the data lane, which is clock and data, and it's I2C, and it sends out 8 bits, and there's a start and an end, and all of those things that you find in I2C. Although it can be modified to become I3C or I cubed C, and with I3C it becomes almost like USB like. It's basically I3C to I2C is USB to UART. So it's 2 lines, and then they introduce a control interface so that you can do some multiplexing, and you can have multiple devices on either side speaking to each other, and basically that's it. They added a control interface, and later, maybe at some point we'll find some time and we'll look at I3C and such. But it's just USB basically. It's what I can say. So, any questions so far at the moment while I take a sip of water? Any questions? I'm willing. Any questions so far? So we're basically close to that. So this is some sort of image that explains to us how data is transmitted, and you basically have a transmitter and a receiver, and the transmitter could be something like a camera, and the receiver could be something like a screen or some sort of microcontroller. And what happens is you sample stuff, you park from pixels to bytes, and then you do some low level protocol, and then this becomes a multiplexer, the HSLP that we've seen, and then that goes into the physical layer, and then from the physical layer it goes to the physical layer of the other side, and it just goes backwards. It's again lane management, low level protocol, and then it does the opposite it did on the other side. So it converts from bytes to pixels, and then it just gives out the data to the receiver. And let's read it here. So byte pixel parking and parking layer, the CSI2 specification supports image applications with varying pixels formats from 6 to 24 bits, but 8-bit pixels are transferred unchanged by this layer. Low-level protocol layer includes the means of establishing the bit level, byte level synchronization for serial data transferred between the start of transmission and end of transmission events, and also includes assignment of bit value interpretation such as endian assignment and such and such and so on. So basically, what am I saying here? Or what are they saying? What they're saying is MIPI is a lot of agreements working together. It's a lot of glue working together. So there's a way to do the wiring. There's a way to do the signals. There's a way to use the slew rates. There's a way to use the clocks and all of those things. And when all of those things are put together, you end up with this thing stacked. It's stacked in such a way that you can run images and screens to read. And then CSI2 is lane scalable for increased performance, and depending on the bandwidth of the application, the number of data lanes may be 1, 2, or 3, or 4, and transmitting side of the interface distributes bytes from the outgoing data stream to 1 or more lanes. So what it is saying is that the camera here, the IMX219 here, the Sony IMX219 that transfers to this. What this is saying is there's a lot of electronics. It's not just plain wires all the way here. The image actually goes into some electronics here, and it is converted into some sort of data signals, and then it is sent through this FPC cable into the microcontroller. And then at this point, there's also a deconversion or a demodulation on this side that happens, and then the microcontroller can consume it. And this is the difference between something like that and something like this, which does not have MIPI, but it has like straight wires from the sensor into the microcontroller, and those wires perform through some image interface called SDMA by NXP. Yeah, any questions so far? I feel like I'm going really fast, but I'm not so sure. Maybe I'm going too slow. Any questions? Any comments? Anyone who wants to make fun of me? Oh, Mr. Original has shown up. Hi, Bartholomew. How are you today? What are you doing today? I'm going to take a break and ask you a few questions before we go on. Bartholomew is around. If Bartholomew is around, it's going to be a good day. So yeah, Bartholomew is around, and he's really good. He always speaks. I like it when he speaks. Cool. So that sort of gets us all the way through to through MIPI and CSI and DSI, and now we're gonna look at like image sensor basics. And this is something that nice. Hi, Bartholomew. Bartholomew just joined. Basically, we've been going through this thing, and we're trying to just understand how MIPI works, and not even just MIPI, just image sensors. Hi, Erdal. Hi, Erdal. Hi. I don't know. I wonder if I'm saying your name right. Erdal. Hi, Erdal. Welcome to the stream. Thank you so much for joining us today. It's amazing to have you around. Please feel free to ask any questions you have, and we have in the description we should have a link to the Discord and such, and you can join us and see what's happening. Yeah, cool. And I'll add a link to the thing that we are going through in the description while people are here. Yeah, so there's that, and then join the community. And today we're not working on any code, so perfect. Okay, amazing. So feel free to ask any questions. Feel free to wonder. Feel free to tell me if my audio is too low or something, or I'm going too fast. Feel free. Cool. So now we want to think about how image sensors work. So you have a camera like that. How does the camera actually work? So usually they have something called a color filter array. But what a color filter array is basically arrangement of ADCs with certain filters. Okay, so there's an ADC that is filtered to get green light or green wavelength, and there's an ADC that is filtered to get red wavelength, and there's an ADC that is filtered to get blue wavelength. But sometimes these days of more recent things have become more complicated, that you can get something like cyan and magenta and all of those, but really it's red, green and blue, and you mix this up and then you get so there's a Bayer filter, there's a RGBE filter, there's a IYYB filter, there's a CYYM, CYGM, RGBW, I don't know which one that is, RGBW. These are all color filter arrays, and these are all arrangements of you can assume them to be tiny analog to digital converters that are tuned. They're all tuned. It's Bartholomew's favorite thing, filtering and signal processing. They're all tuned so that they are sensitive to some certain wavelengths. Okay, so one is tuned to it's sensitive to a green wavelength, and another one is tuned so that it's sensitive to a blue wavelength or a red wavelength, and that makes something called a color filter array. And this is actually what image sensors do. They just this is also what, strangely enough, this is also somewhat what your eyes do as well. You look at the world, it absorbs wavelengths of light, and then depending on this wavelengths of light, it just does this compression or basically collation of information so that it can make either a color or a shape or an edge or something of the sort. Yeah, Bartholomew, we know you love filtering. Yeah, Bartholomew. So basically, the cameras or image sensors are just a bunch of ADCs or tuned to filter out different colors, and then they are arranged in a certain array so that you can collect colors coming in and you can compress them into colors. And if you want to look at how this is done, there's a library called libmpix.org, or rather libmpix, and you can go to its GitHub and you can look at how we can look at debayering. Let's look at an op debayering. Let's look at the source and then look at debayering and op debayer. So let's look at one by one. Maybe this is probably going to be a black and white. And basically, what you're going to do is this is actually too simplistic, to be honest. I want to look at a bit of a more complex one. Let's look at a 2x2. So a 2x2 is a square of 4, and then you combine all of those 2x2. You basically combine a 2x2 is 1, 2, 1, 1, 2, and you combine all these 4 into one pixel. Basically, is what happens. That's what is a 2x2. And if you want to look at how it happens, you can come here and you can see what happens, and you can see how colors are made from groups of colors, basically. But in essence, it's what we did. If you ever did a very elementary art class, it's just you mix this color and this color and this color, and this is what you get. libmpix is already a Zephyr module. libmpix is already a Zephyr module. Zephyr external modules. libmpix is a Zephyr module, and it's I'm going to just a moment, Bartholomew, just so I can explain it to you. But libmpix is so I think external modules, module repository, links to modules. Where is external modules? Where is it? Modules. Where can I see the external modules? Let's see. Yeah. So libmpix is an external module, but I think what Bartholomew is trying to ask about is libmp. Libmp. They're not the same thing. But Bartholomew, libmp is not libmp RFC. Yeah. No. So Bartholomew is trying to talk about, let me see, Zephyr. This is good. This is a break from me just talking. Bartholomew is talking about libmp, and libmp is not libmpix. This is one of them is a media pipe, and another one is an image signal processing one. So libmp. Such. Yeah. So this is what Bartholomew is referring to. Lib media pipe. So one of them is in charge of actually taking bytes and making them pixels, and another one is in charge of enabling you to do the kind of thing I'm doing right now, which is taking multiple streams of images and combining them into something. I had this confusion earlier as well, but I'm going to pause until Bartholomew tells me he understands the difference. So one of them takes bytes from your cameras and makes them an image, and then another one takes buffers and allows you to combine buffers into a stream of some sort. So they're not the same at all. They actually don't do the same thing. Does it make sense, Bartholomew? You can ask questions before we go on. I'm going to pause here until Bartholomew says it makes sense to him. And if anyone else has questions, you can also ask right now before we go back to the thing. Yeah, nice. Okay, good. So Bartholomew understands, which is what I wanted to know. So they're not the same thing. One is an image signal processing thing, another one is a media pipe. Even though they they happen to just have like their names are so the same. It's like libmp, libmpix. So no, they don't do the same thing. Cool. Okay, so let's go back to this. So basically, this is what is being explained here is what libmpix does, which is take ADC readings from, because a camera is just an ADC. A camera is just a bunch of ADCs, and it gives you all of these readings, and then one reading corresponds to a green or a blue or a red, and all of and so on and so forth. And then you can compress all of this into a bunch of pixels. So you usually have if you're getting if you have a, say, 10 by 10 megapixel camera, it means you're getting 30 by 30 megabytes of data per image, and then you compress this by a third. You shrink it by a third, because 3 bytes from 3 bytes become 1 pixel. Okay, a pixel and a byte is not the same thing, because it takes like 24 bytes to make one pixel. So you do an averaging of some sort, which is what I was trying to show here. You do an averaging of some sort, and then you join a number of bytes into 1 pixel. Basically, that's how an image sensor works. Okay, but an image sensor and a camera sensor is not the same thing, because a camera sensor implies that you're getting an image out of it, and an image sensor gives you just gives you a buffer. It just gives you a buffer out, if that makes any sense. Okay, so what is being shown here is how an image sensor Okay, let's read here. An image sensor contains an array of photosensitive elements. There you go, ADCs. Each element converts light into a raw pixel, and the OV5640 has a pixel array of 2464 columns by 1964 columns. Not all pixels are used for image capture. Yes, you also have like borders, and you have like dark ones, you have like reference pixels and such. As shown in the previous image, active columns are 16 to 2607, and the active lines are 14 to 1957, and the maximum usable image array is 2592 by 1944, which is 5 megapixels. An ADC on the image sensor samples the voltage of each pixel one at a time, outputs a digital value on a data bus. The bus width is equal to the ADC resolution bit depth, and this unprocessed digital value is known as a raw format. And the OV5640 has a 10-bit ADC and a 10-bit wide data bus. So outputs are in the native row 10 format. Image sensors can range in resolution from 6 bits or all the way to 24 bits. ADCs read the value of each pixel across an entire line, moves to the next line, repeats the process until the entire pixel array, which is a frame, is read. And a frame of raw images go through a series of post-processing steps, such as demosaicing, color correction, white balance, before it is considered usable or pleasing to the eye. These algorithms are either handled in the image sensor or during post-processing using an image signal processor. This, if I could get my mouse, this is libmpix, Bartholomew. Only that. Okay? So this is libmpix. It just does you give it bytes, it gives you back pixels or some color filter or some color space of some sort. Okay, and then let's look at what video streaming is done. So how many more things? Okay, cool. So video stream, image sensor, video timing. This is quite important when you start. It's actually, this is where a lot of things can get very confusing. Because if you don't get this, and it's quite easy to get as well, but there's so many words that I use, special words that I use, that it sometimes becomes very confusing. So, video stream. Most CMOS camera, what is this? What is it? Composite metal oxide, something like that. Or what does CMOS mean? Something metal oxide. Most CMOS image sensors can be programmed to generate single images or a video stream. It helps to have a basic understanding of how digital displays work, to understand the data transfer, formatting, timing, data transfer, formatting, and timing. All modern computer displays are raster displays, meaning the display image is created by writing one line at a time, pixel by pixel, from left to right, and from the top of the display to the bottom of the display. The displayed image or frame is composed of a rectangular array of pixels. A video stream is composed of a series of frames displayed at a fixed timing interval, and this timing interval can be described using the frames per second, or FPS, or hertz. So 60 hertz or 60 FPS or whatever FPS you use, that is how many frames are coming to this display at a given time. In essence, what this thing is saying is there's really no such thing as, I wonder if I can hide this part so that it can move that way. Yes, so that my face is not in the way of this. Cool. So what this is saying is that there's no such thing as video really. What exists is a series of images. And then depending on how quickly you swap out all those images, you get some sort of frame rate or some sort of image rate or some sort of hertz. Okay? And then it goes on further to break that down and says there's no such thing as an image. You only get a line of pixels. Excuse me, which is a row. And then it goes even further to say that there's no such thing as a row. It's actually an arrangement of pixels, and each pixel is updated one at a time. Okay, so you update pixels at a certain speed, and it depends on how long it takes you to update the whole screen. And for 60 FPS, the whole screen is updated 60 times per second. So you're swapping complete frames per second, which means you're swapping bytes at pixels at a much faster rate, and so on and so forth. And the way you do it is you do it line by line, and then the updater moves line by line, all the way to the bottom, and then it skips to the top, and then it goes all the way to the bottom, and it skips to the top, and such and such and such. And there is a video that I would like to share from the 70s or something. Let me see if I can find this video, and I can put it in the link in the description. But basically the video was how TVs work. How TVs work video. Yeah. How television works. Videos. There's a newer one. FPGA graphics. So I think there's a video, there's a thing here that I want to share. Beginning FPGA, no, I want to share something. The secret life of the television. Yeah. So there's this video. It just basically explains how these things came to be, and it's been remastered, and it's done by Tim Hamke. This is an amazing video to watch. It explains this thing much better than I could explain it, and it takes things back to basics. And once you understand them at the basic level that is this, it becomes very easy to extrapolate them into something like an RTOS, an FPGA, or whatever way you want to do it. And I'm gonna actually add it to the description of the video today, so that later and in the meanwhile people can ask questions. How's this? The secret life of television. The secret life of television. Okay, cool. So if you have a chance and you have half an hour of your day and you really want to find out, go check out the secret life of television, and it will really explain to you how it came to be that TV started working this way, and how this is now more or less digitally done. We actually end up using address spaces. We use memory mapped addresses, and we update memory mapped addresses in a certain way. But usually it used to be a moving electron beam before. That's what made CRT TVs. If you're old enough to know that, some of you will have been born in a. And if this video lasts long, this is probably if you're playing this 10 years after I made it. Some of you will have been born without CRTs existing, and you'll only know about flat panel TVs and such. And if you're learning later on this, and this is how things came to be, and this hopefully this information still lasts. And yeah, I'd be glad to if it was found. Yeah, so I'm gonna take a sip of water, and then we can go on a bit. We're almost done, really. But once you understand these basics, image sensors become really straightforward, and it's all about repeating, and then they become really simple. Any questions at the moment? I'm supposed to drink close to 5 liters of water per day. Okay, cool. So, the horizontal retrace is not exactly instantaneous. It doesn't just move to the other side, of course. There's a certain amount of time required to move the beam from like the end of the line to the beginning of the next line, and these times are called porches. So there's something called a horizontal front porch, and this is the time, I think it's before the row starts. And then there's a time called a horizontal back porch, and this is the gap of time. You can consider it a padding. Again, we can go back to FPGA graphics. So it's easier when you see these things really labeled up. So if you look here, here you go. So there's a back porch before the row, and there's a front porch after the row, and then there's a sink here. And then there's a vertical back porch before the frame, and the vertical front porch after the frame. And then there's a sync period here. And this green period can be used for other things. You can use this time to transfer audio. You can use this time to sync, to edit things, and such, and so on and so forth. And if in case you're wanting to like widen images and such, or like sample different sensors, you can make it so that this gap is big enough that you can fit another active pixels here, and then you can make like really wide. Consider something like VR or something of the sort, or 360 videos. You want to make a 360 video, and then so you use these paddings to actually join other images, and then you can make a 360 video and such. Cool. So that is what there's a front porch, there's a back porch. So the front porch is the one that is after, and the back porch the one that is before. Okay. And this is both for the vertical, which is the frame, and for the horizontal, which is the row. and so on and such forth. And these are signals that you're going to encounter. You're going to encounter a frame called a F-sync, and you're going to encounter a frame called a V-sync. And a V-sync is basically to tell you that, if I remember correctly, the frame is done, and a H-sync is the one that tells you a row is done. You probably are only going to care about the V-sync because most sensors today will actually do H-sync for you. But if you go low enough into these things and you're not developing a camera, you're actually developing on top of an image sensor, then you're going to have to deal with this H-sync and V-sync things and frame sync and such. And also when you start developing things like computer vision and you're wanting to combine images or things of the sort, you're going to, this sort of terms are going to become. The work is not difficult, it's really the names of the things. Once you know the names of the things and you know where to plug them in, just like mathematical equations, once you know the formulas and you know where to plug them in, things become really simple and really straightforward. Okay, cool. So, modern digital displays, as I was saying, because we use address spaces, modern digital displays no longer need time to steer an electron beam around, but they still make use of these blanking periods for things like image processing, sending additional data, audio in the case of HDMI, or embedded image data, things for like CSI2. You can tag things. You can. It depends on what you want to do. Image sensing and computer vision are really. This is stuff you can do quite a lot with. Especially unfortunately in times like today where there's wars going on, and you need machines to sort of be able to see and decide what they're seeing. So basically, as you can see here, this is the total display area, and then there's a back porch, and there's a front porch here, and there's a back porch here, and there's a front porch here, and you can use all of that time to send other signals, like explained in HDMI. You can use that time to send audio. You can embed that image with some data, or you can basically be doing things like image signal processing, and you can do things like overlaying or memory to memory stuff, and it depends on what you end up wanting to do. Okay, if anyone has any questions, please feel free to ask them. I'm here for that. A single horizontal line of image data is signaled by the assertion of the H-sync. Basically, what this says is when H-sync goes to high, you have gotten a row, and also means that when V-sync goes to high, it has completed a whole thing downwards, which is you have not gotten a column, you have gotten all the columns, because all the rows will happen. It does row by row, so by the time it tells you you've gotten a whole column, it means all the columns are done as well. And then you have a pixel clock, which is a peak clock, which is something we looked at here. Remember here, peak clock, this is a pixel clock here, or a peripheral clock. It comes in many names. And a pixel clock is used to, a clock must keep the pixel data and synchronization signals in order. This clock is known as a pixel clock. A single pixel is transferred on every clock cycle, and this is the primary clock for most image display transport systems. In the case of image sensors, the pixel clock time period sets the time interval for the ADC and the conversion of each pixel clock, and it is the root clock for H-sync and V-sync clocks, and H-sync signals and the start and of each line and V-sync line. So basically, there's going to be a number of clocks, especially when you start doing dealing with raw image sensors. You're going to realize there's a master clock, there's a P clock, there's an X clock. Like on my OV640, there's a P clock and there's a master clock, and then there's other cameras. There's other cameras like the IMX219. Let's see. IMX219 pinout. You will find that it might even have more clocks than the 7640. So let's try to see how many pins it has. It doesn't show the pinout. Let's see. I'm basically looking for something that will show us the pins. But varied image sensors will have varied clocks, and you can use all of these different clocks in different ways. Basically, is what is the story. And basically, a pixel clock defines how long it takes to sample a pixel and all of those things. And then there's CSI2 video timing. And this is more than image sensors now, because now we are looking at media pipes and all of those things. And the CSI2 low-level protocol turns pixel data, VSync and H6 pulses into series of packets. And the packets are sent over the physical DeFi interface while maintaining the critical timing parameters related to each other. So what is this saying? When you get to the pixel clock, the master clock, that is this layer. It's just in the image sensor, okay? So let's look at a more rudimentary one. So you see this one. This is not using. There's no CSI cable here. This is just raw lines into the MCU. This uses SDMA, not CSI. But what this is saying is, because you have CSI on this, you have a CSI connector here and into a camera here. So basically, this image, this microcontroller or this system here, the N6570, can actually do a lot of the video transfer for you, because it knows when a row has been done, it knows H-sync, it knows V-sync when a frame has been done, and because it knows also what pixels you're doing, it can send you frames. And because it can send you frames, it can do video timing, which means it can send you video signals. It can send you a bunch of frames, one after the other, and this can become videos, and so on. And again, here there's going to be, today what I wanted to do is look at image sensors, not actually MIPI itself or such. So if you want to dig into how it does it and such, this is going to be a good thing. So you can look at the MIPI packet data and determine how it's arranged and what is arranged and what is sent when and how it's sent when and such and so on and so forth. Okay, so here we kind of went backwards. Pixel byte parking, and this is what they're saying here is old image sensors predating the CSI2 standard use a parallel bus to output the ADC data to a SoC or a dedicated image processor. So this kind of image sensor uses a parallel bus because it's D2 all the way to D9, and this is an 8-bit parallel line that is sending data, straight to the, just the same as I've shown you on the MCX N236 a Freedom board. It's not using CSI. It's just the wire is going straight into the system on chip or the MCU, and the MCU is consuming that and working on controlling that. The thing that happens then is that the image moves at a much slower pace compared to MIPI, and that actually, but MIPI is a big machine. It's like a Ferrari engine. It's got so many things on it that it's very hard to pack it onto. It's very hard to pack it onto a microcontroller. Also, remember, MIPI can move data at gigahertz speed, and most microcontrollers are not working at gigahertz speed. So you have to consider this. So pixel and byte parking is the thing that we looked at when we looked at the color filter arrays. That's how the bytes are arranged and how you consume them and how it makes a pixel. So exactly. So I think that's the end. So there's a description of the clocks. There's a master clock, often defined as an M clock. So it's not there. But you can also define it an X clock. This is the master clock, often defined as an M clock, is a timing signal using camera devices to synchronize various internal operations of the camera sensors, such as pixel readout and analog to digital conversion. Okay, and then there's a pixel clock, which is used for the pixel timing. And then if you're using MIPI, there's a MIPI clock itself, and the MIPI clock is used for MIPI timing, and this one is often in the gigahertz range of speed. So thank you all so much for showing up today. That has been a good exploration of image sensors, a bit of MIPI, a bit of video, a bit of television. And I wonder, does anyone have any questions currently? Before we wrap this up. Really. Does anyone have any questions currently? Any wonders? Any doubts? If anyone has any questions, wonders, or doubts, then I can always answer them. Anyways, thank you so much for showing up today. It's been amazing to have all of you around. If anyone has any questions, please feel free to join our Discord community and discuss with us and kind of learn with us. And yeah, it's been amazing to go through image sensors, MIPI, and how they transfer data, and understanding all of this and bringing all this together into a usable space. Thank you so much. My name is Zach, and this is Guy Ochos. See you next time. Remember to be daring. Cheers.